Okay, we're on Unit 3, Activity 1, Relative Mass, and we're going to be getting the relative mass of different kinds of hardware. We're going to take a look at some washers in a container, some hex nuts, and some bolts, and we're going to learn to count by massing, and then we're going to apply what we've learned to the particle model of matter. I'm going to first get the mass of this empty container. The mass of the empty container 9.872 grams. And then we're going to get the mass of the other pieces of hardware in their containers. Let's first start with the washers. $27.192. And then we're going to move to the hex nuts. 33.781. And then we will move to the bolts here. 62.106 grams. Now, if we want just the mass of the hardware, if we think of this container as being A and the mass of the container and the hardware being B, if you want the mass of just the hardware pieces, you're going to take B minus A. So you need your calculator. You're going to take 27.192 minus 9.872. This is 17.320 grams. Remember, when you're adding or subtracting, you look for the fewest decimal places. Each one of these goes to the tenths, hundredths, thousandths place. So you have to record this to the thousandths place as well. 33.781 minus 9.872. This is 23.909. And then 62.106 minus 9.872. This is 52.234 grams. Okay. Now, if you look at question number 1 under the analysis section, it says, you weighed samples of multiple pieces of hardware. If each vial contains the same number of hardware pieces, which individual piece of hardware do you think is the most massive? Well, here we have 52.234 grams for the bolts. That is the greatest mass out of the 3 pieces. Therefore, this would be the most massive. And then, which would be the least massive? Well, this has the lowest mass out of the 3, so this would have to be the least massive if we have the same number in each, because if I have a certain number in the container and I divide by that number, this will give me the largest mass per bolt. This will give me the smallest mass per washer. Okay? Number 2, calculate the relative mass of each kind of hardware. To do this, divide each mass by the smallest mass item. So if I divide this by itself, that will give me, and when I multiply or divide, remember I'm looking for the fewest number of sig figs, this is 5. That will be my relative mass. If I divide this by 17.320 grams, and then this also, that'll be 1.3804. And then this is 3.0158. Okay? So now, if I turn to number 3 on the next page, it says you go into a hardware store and you find a box of washers, hex nuts, and bolts. Each box says it contains 250 pieces of hardware, which is the heaviest. Well, if you look at the relative masses, this is the relative mass of each piece to one another. So the washers, the box of washers should be the lightest, and the box of bolts should be the heaviest, because this is the mass of each individual piece, so to speak, relative to one another. Okay? If you take a look at question number 4, another hardware store sells hex nuts and bolts by the bag. Each bag contains a kilogram of hardware. The clerk wants to sell you a kilogram bag of hex nuts and a kilogram bag of bolts to complete a project. Why is this a bad idea? Well, beforehand, I had the same number. For instance, each one of these containers has the same number of each piece of hardware in it. Okay, so I'm determining the relative masses to one another. But if I get a kilogram of each piece of hardware in a bag, I'm not going to have the same number. So it means I will inevitably run out before I can use everything. So what will likely happen is you will have more washers in a kilogram than you will bolts. So you will run out of bolts, or you will have more hex nuts in a bag than you will bolts, and you'll still run out of bolts because they have a much higher mass. So this is a very bad idea. If the clerk in number 5 still wants to sell you a kilogram bag of hex nuts, what mass of bolts would you need so that you had enough bolts for all of the hex nuts? Well, if you have a kilogram of hex nuts, let's switch this, since these are in grams, let's switch this to, let's switch this over to grams. There's your one-step metric conversion. And then since this is hex nuts, I'm going to take this relative mass of hex nuts and then this relative mass of bolts. And then I'm going to get my calculator. And that's going to be 2,185. Let's see, let's round this to 2,190. Let's just follow sig figs. So that's the mass of bolts that you would need so that you had enough hex nuts. Well, if I wanted to equate that to kilograms, you could convert this back if you wanted to. So it would look like that. That's your one-step metric conversion. You're going to get 2.19 kilograms. Okay, so that is how many kilograms of bolts you would need so that you had enough bolts for all of your hex nuts. Okay. Now, if you take a look at the next page on application, relative masses of atoms, it says, imagine you could shrink yourself down to the atomic level. You're holding an atom of carbon in one hand and an atom of magnesium in another. How do you think the masses of each atom compare? Would one be more massive or less massive? So take a look at your periodic table. And if you look at the box where carbon is on the right-hand side where the nonmetals are, the average mass of carbon atoms is 12.01, and the unit is AMU, atomic mass unit. If you look at magnesium on the left-hand side of the periodic table where the metals are, it's in the second column there. The average mass of magnesium atoms is 24.31 atomic mass units. So it looks like the mass of a magnesium atom is 2 times that of a carbon atom. And if you took these and you made a ratio, you did 24.31 divided by 12.01, you're going to get around 2. So the mass of a magnesium atom is 2 times the mass of a carbon atom. Now, since we can't measure individual atoms on a balance, the masses were assigned to the elements to make comparisons really straightforward. Hydrogen is the lightest element, so it has an assigned mass of 1. Oxygen gas is 16 times that. It's 16 times as heavy as hydrogen gas, so it has a relative mass of 16. In the simplest compound of carbon and oxygen, the mass of carbon is 3/4 that of oxygen, so carbon was assigned a relative mass of 12. In the simplest compound of magnesium and oxygen, the mass of magnesium is about 1.5 times greater than that of oxygen. So it was assigned a relative mass of 24, and so on. So the numbers are known as mass numbers on the periodic table of the elements, and we will be using them in units of grams. So if you examine samples of magnesium and carbon, you would see that carbon is sort of a dark gray black powder, and it looks smaller. Magnesium looks bigger, it's more massive, and you can see that in the pictures on the handout. Number 1 says, how do equal masses of different elements compare? You're in the lab, and you measure out a 10-gram sample of carbon in one beaker, and a separate 10-gram sample of magnesium in another. How would these samples of matter compare? So you have 10 grams of carbon, 10 grams of magnesium, and they are in containers. So the carbon is going to be a fine powder, really small particle sizes. The magnesium is going to look like these giant chunks. Of matter, okay? So this will be 2 times the mass of this. So there will be half as many atoms in 10 grams as carbon atoms. Okay, now if you take a look at the next page, it says, how can we get samples of different elements that have the same number of particles? If you measured out a 10-gram lump or pile of carbon atoms on a balance, what mass of magnesium lump or pile would you need to measure so that both lumps have the same number of atoms? Well, you need 20 grams of magnesium to contain the same number of atoms as 10 grams of carbon. And that's because the mass of magnesium is 2 times that of carbon. So on the periodic table, remember, carbon was 12.01 and magnesium was 24. Okay, so this contains the same number of particles or atoms. So piles of atoms or particles with the same number of particles is actually referred to as a mole. Okay, it's a quantity that we use in chemistry, sort of like a unit of measure, like when you're baking, like a dozen is 12, half a dozen would be 6. But in chemistry, particles are so small, we have so many particles within a sample that we needed something that was a lot greater. So we refer to it as the mole. And the mole technically is defined as 6.022 times 10 to the 23rd things. All of the masses on the periodic table are referred to as a mole of that element. So how did this come to be? Well, a pile of carbon atoms, 6.022 times 10 to the 23rd carbon atoms would be 12.01 grams. So on the periodic table, if you relate all of the masses of each element to this concept, that means that this mass on the periodic table for each element would also be a mole, okay? Number 3, in the empirical formula of a compound lab, we'll be exploring the relationship of how much mass there is versus how many atoms there are in a sample of a compound. Consider a common compound, everyday table salt. So table salt is sodium chloride. Sodium chloride has a chemical formula of NaCl. A 100-gram sample of table salt contains 39 grams of sodium atoms and 61 grams of chlorine atoms. Does this mean table salt contains more atoms of chlorine? Why or why not? Well, the mass of a sodium atom is 22.99 grams, or atomic mass units, or 23 grams on the periodic table. And then chlorine is 35.45 grams, or atomic mass units. So if you take this ratio, 35.45 divided by 22.99, or 23, you're going to end up getting around 1.5. So what does this tell us? This tells us that the mass ratio of chlorine to sodium is 1.5 grams of chlorine for 1 gram of sodium in sodium chloride. Okay, so if we take the 61 grams of chlorine divided by the 39 grams of sodium in the problem, you'll get a ratio of 1.5. So no, it doesn't mean that we contain more atoms of chlorine, because the mass ratio is 1.5 grams of chlorine to 1.5 grams of sodium. Now, your homework is to do Unit 3, worksheet number 1, how much mass versus how many moles, and then I'm going to take a look at a couple of those with you right now.